Alright, welcome back to the third lecture in CSCE 642, Reinforcement Learning and Deep Reinforcement Learning. Today's lecture is going to cover chapters 3 and 4 out of our textbook. Today we're going to cover Markov decision processes, so we're going to generalize the multi-armed bandit problem that we've seen in the previous lecture to apply for environment with a set of many possible states that we transition between those. And we'll also start discussing a simple approach to solve an MDP, which is dynamic programming or solving. We'll see how to solve the MDP offline while assuming to know the model. It's a simplifying assumption, and later we're going to remove it, but for now it will help us get started. So, some reminders regarding your duties. So first of all, the quiz on multi-armed bandit is available on Canvas. Please complete it by the date that is specified on Canvas. Also go over the tutorials, the linear algebra, basic probability, Python, NumPy, and Gym or Gymnasium tutorial. Please be sure to cover those before we move forwards towards implementing your home assignments. Project, please go over the project description on the course website and the timeline. Also, please find a partner. And as I said earlier, there is a relevant discussion board for finding partners on the campus-wide discussion board for this semester. Okay, so how is today's lecture? How does it fit in our high-level flow of this course? So we already discussed the stateless decision process, right, with the multi-armed bandit problem. And today we're going to generalize that to the full MDP. We're going to transition between states, and each state might require a different action. So we're trying to, there's a different optimal action affiliated with each one of the states. So now we have to converge on a state-dependent policy, define that. We'll discuss the conditions for solving an MDP. How do we solve it? How do we find such an optimal policy? And we'll see, as I said before, a simple way to solve an MDP using dynamic programming. This is an offline approach to solve MDPs. Offline meaning that we don't really interact with the environment, so it's not really reinforcement learning. But the concepts that we're going to cover using dynamic programming will be relevant later on when we drop the assumption that we know the model. Question? Yeah.
Yes. We studied that even for a stateless decision process, we did use temporal difference, right? So would there be a connection here?
Yes. There definitely will be. Yeah. We'll see it later on, right? The temporal difference is now state dependent. Well, previously it was not. It was in a stateless case. But we'll get that later on, right? Okay. So let's introduce states into the problem that we're trying to solve. So previously when we discussed the multi-armed bandit problem, we chose an action, and at each time step we observed the reward, and then we were faced with the same problem over and over again. We chose again, maybe a different action, maybe the same action, we observed the reward, and we try to learn from the observed rewards regarding the optimal action. In an MDP, we assume that there is an agent that is acting in the environment, right? As I said previously, for today we want to assume to learn while interacting with the environment, but later on we will. But in any case, once we have a policy, once we optimize the policy, the assumption is that the policy is used by an agent that is interacting in the environment. Okay? So we train a policy for an agent that interacts with the environment. And later on when we discuss reinforcement learning, the training itself will also be while interacting with the environment. Done? Okay. The environment includes a set of possible states now, and we will transition between the states. The agent will transition between the states. At each state, a different set of actions might be applicable. That might be the case, but not necessarily. Each state action pair has a different expected outcome. So if I'm in a specific state, we'll see example of state space later on, and I take a specific action, I will observe a specific immediate reward, and also I will arrive at a new state in the environment. And there is a distribution, there is some uncertainty, or could be uncertainty with respect to the reward that I'm going to observe, and the next state that I'm going to arrive at. Now, it's not necessarily the case. We can still use reinforcement learning if in deterministic environments, but in such cases, usually we have other AI tools that might be more relevant. So for the most case, we will assume that at least the transition between states is stochastic. Okay, so now our interaction with the environment will look as follows. We'll be at a state, we'll take a specific action, observe the reward, and then we'll also observe the next state that we arrive at. From the next state, again, we'll choose an action that we will apply in the next state, observe the reward, and so on. This process will continue. So here we're going to learn from transitions, which are current state, a specific action, a reward, and the next state. Now you might ask yourself, well, shouldn't we learn, is this transition sufficient in order to do efficient learning or meaningful learning? Don't we need to take into account the previous states that we visited prior to this transition, or the states and actions that we're going to observe in the following transitions? And the answer is no. Why is that?
Well, that's because they follow the Markovian property.
That's because, right. So the outcomes for each state and actions are independent of the previous state and actions, right? Due to the Markovian property, the probability for obtaining a specific reward, for observing a specific reward or a specific next state, is dependent on the state and action that we currently are at and the action that we currently took, and is independent of all of the previous states. Okay, that's the Markovian property that we discussed before. So let's look at an example of an example MDP, and this example will follow it through this lecture. So let's assume that we have a robot that lives in a maze-like environment, right, in a grid. So the agent lives in a grid, and there are walls that blocks the agent path. Okay, these are just the boundaries, and also we have like some obstacle here in the middle. The agent, we also assume that it follows some noisy movements. So it can move to any of the cardinal directions, but it doesn't always go as planned. So the robot might slip. With probability 0.8, the next state, the agent will follow the intended action. That is, if the agent is trying to go north, with probability 0.8, it will actually succeed in going to the grid cell above it, right, or to the north. However, there is a 0.1 probability for slipping to the left, and there is a 0.1 probability slipping to the right. If the robot is trying to go north, these probabilities will be affiliated with the arriving at the cell to the west and the cell to the east. If there is a wall in the direction the agent would have taken, we'll just assume that the agent stays in place. Okay, so if the agent at the current position will try to go south, try to go down, if it's here and try to go down, and will actually succeed in doing that action, it will simply stay in place. Right? I mean, succeed, that is, it actually performed the intended action. Okay, and so we also have some immediate rewards, a reward function. The agent will receive reward each time, for each time step. So there is a reward, an immediate reward of minus 0.1 for each step, regardless of where the agent is and what action it took. And this can be conceptually viewed as a living reward or some battery loss, fuel loss for the agent. However, there are two significant results at one of the terminal positions here. If the agent arrives in this position, it receives a +1 reward. However, if it will fall in the pit here, it will receive a -1 reward, and the game will be over in either case. The objective, as always, is to find a policy that is an action, a preferred action to take at each one of these states, such that the accumulated rewards over time steps will be maximized. So in a more general sense, an MDP, any MDP, will be defined by the set of states. So in our case, this will be all of the possible grid cells here. These are the states that the agent can be in. Now, of course, it can get much more complicated than that. For instance, if our agent had specific fuel levels or battery levels, it would have can you think of other attributes that might be included in the state space for our robot here?
Would it see the obstacles and would it see what's around it, the environment around it?
So we might add some sensing assumptions. Anyway, all of these go into the state representation of our robot. Then our robot has a set, or MDP, our RL agent will have a set of available actions. And again, these might be defined over the entire state space, or it can be a function of the state itself. That is, in some states, some actions might be applicable and some might not. So we can either have this as a set of function, or a set of action, or sometimes a function mapping states to a set of actions. Then an MDP has a state transition probability function. We'll denote it with as the following probability. This will be the probability. It will represent a specific value, which is the probability of arriving to a state S prime, given that we are currently at state S and performed action A. This is also known as the model dynamics. So, discuss model dynamics, we also mean the state transition probabilities. The MDP also includes a reward function, which is a mapping from state, a specific state, a specific action, and the next state to a utility value. It's a single value. This represents the utility gained from arriving at state S prime after performing action A at state S. In many cases, you'll see in the literature the reward function as a function only of the current state and the current action, or even just a function of the current state. These are, of course, all over generalization of this function, right? It just ignores the next states, for instance. And for many applications, it is sufficiently rich to represent what we actually want to, the reward function that we actually care about. I would say, what is the most common one that you saw in the literature so far?
Just a function of the previous state and action.
Right, I think this is the one that I've seen mostly in the literature. But all of these are valid ways to represent your reward. Then the MDP should also define a start state, or in some cases this might be defined as a distribution over the initial locations, the initial states, from where the agent starts its episode. And maybe sometimes we might have terminal states. This is not a requirement. We do have continual problems with what they just assume to continue forever, and that's also fine. But in some cases we do have terminal states. For instance, in this example here, right, as we said before, these two states would be terminal states, after which the process ends.